Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The publication in 1696 of the Marquis de L'Hopital's analysis of infinitely small quantities for the understanding of curved lines represents a pivotal moment in the history of mathematical thought. It stands as the first published textbook on the differential calculus, a work that translated the esoteric insights of Leibniz and the Bernoullis into a systematic and accessible analytical engine. The immense influence of the analyse derived from its clarity, its algorithmic approach, and its confident application to a host of geometric problems that had confounded previous generations. A direct evaluation of the work's internal claims, proceeding sequentially through its structure, reveals a treatise of remarkable pedagogical power, one whose profound practical successes were built upon foundational postulates of an intuitive, and at times precarious, logical character. This examination will proceed by evaluating the core arguments and mechanisms presented in each significant part of the analyse, assessing the coherence of its claims and the efficacy of its methods as presented to its contemporary mathematical audience. The work's genius, we will find, lies in its systematization, a process that made the new analysis a widespread tool, while simultaneously exposing the very foundational questions that would occupy mathematicians for the next century. And Section 1, the axiomatic framework and its metaphysical commitments. The analyse opens with a preface and a set of definitions and postulates that establish the conceptual bedrock for all that follows. The preface itself is a masterpiece of polite scholarly diplomacy, acknowledging the immense contributions of others, particularly the Bernoulli brothers, with a grace that almost obscures the full extent of the intellectual debt. L'Hopital states his desire to give a clear and coherent account of a powerful new method, positioning the work as one of synthesis and instruction. Following this, he lays down two definitions and two postulates that are the absolute heart of his system. The first definition introduces variable and constant quantities, while the second defines the differential as the infinitely small part by which a variable quantity continually increases or decreases. These definitions are intuitive and align with a kinematic understanding of mathematical quantities, the true analytical power a source of subsequent critique. Besides utopoton, the first postulate asks the reader to grant that two quantities which differ from each other by an infinitely small quantity may be used interchangeably. In symbolic terms, this means that the quantity x plus the differential of x may be considered equal to x. The second postulate asks that a curved line be considered as an assemblage of an infinite number of infinitely short straight lines. An evaluation of these foundational claims reveals a deliberate trade of logical rigor for operational power. The first postulate is the engine of simplification for the entire calculus he presents. It allows for the disposal of higher-order infinitesimal terms in calculations, which is precisely what makes the method work. Yet, it contains a profound logical ambiguity. The differential of x must possess a definite, non-zero value to serve as a term in a ratio, such as the ratio of the differential of y to the differential of x. At the same time, it is considered to be zero in relation to the finite quantity x from which it is derived. It is both something and nothing, a useful fiction whose justification is purely pragmatic. Berkeley's later critique of the ghosts of departed quantities finds its primary target in this explicit axiom. The second postulate performs a similar function for geometry. It makes the intuitive notion of a curve's local straightness into a formal principle of analysis. It connects the new calculus to the tradition of Cavaliere's indivisibles, but presents it with the force of an axiom rather than a derived property. The internal claim is that by accepting these two principles, a vast domain of complex problems becomes tractable. The evaluation must be that the claim is true in practice, but the principles themselves are appeals to intuition, creating a system that is magnificently effective and simultaneously built on a foundation that invites deep philosophical and logical scrutiny. Section 2. The codification of differential operations. The first formal section of the analyse is dedicated to establishing the rules for finding the differentials of algebraic expressions. Here, L'Hopital demonstrates the utility of his foundational postulates in creating a simple, repeatable algorithm. He proceeds by examining the differentials of sums, products, quotients, and powers of variable quantities. His derivation of the product rule for a quantity, like the product of x and y, is exemplary of his method. He considers the initial quantity, x multiplied by y, and the infinitesimally increased quantity, which is the product of x plus the differential of x and y plus the differential of y. Expanding this product yields x multiplied by y plus x multiplied by the differential of y plus y multiplied by the differential of x plus the differential of x multiplied by the differential of y. To find the differential of the original product, he subtracts the original quantity, x multiplied by y, from this expanded form. This leaves the expression x multiplied by the differential of y plus y multiplied by the differential of x plus the differential of x multiplied by the differential of y. At this crucial step, he invokes his first postulate, the term representing the product of two differentials, he argues, is an infinitely small quantity in relation to the other terms, and thus may be discarded. The resulting rule for the differential of the product of x and y is given as x multiplied by the differential of y plus y multiplied by the differential of x. The internal claim of this section is that the process of differentiation, which underlies all subsequent applications, can be reduced to a small set of algebraic rules. His evaluation of these rules demonstrates their consistency within the axiomatic system he has established. The derivations for the quotient rule and the power rule follow a similar pattern of algebraic expansion and subsequent simplification. By discarding high-order infinitesimals, the profound success of this section lies in its transformation of a conceptually difficult idea into a mechanical procedure. The geometric intuition of Leibniz or the fluxional reasoning of Newton is here supplanted by a pure, almost thoughtless, symbolic manipulation. For the audience of the analyse, this was its greatest strength. It made the calculus learnable and usable without requiring a deep dive into its metaphysical underpinnings. The critical evaluation of the logic reveals that each successful derivation depends entirely on the legitimacy of that initial, logically challenging postulate. The entire edifice of operational rules is sound, provided one grants the foundational premise that infinitesimals can be selectively ignored. The claim of algorithmic coherence is internally valid, while its ultimate justification remains external to the logic itself, residing in utility of the results produced. Section 3. The geometric application to tangents. Having established the algebraic rules of differentiation, L'Hopital moves, in his second section, to the fundamental geometric problem of the age, the construction of tangents to curved lines. This section claims to present a universal method that supersedes the diverse and often highly specific techniques of Descartes, Fermat, and Barrow. His approach is direct and elegant. He considers a point on a curve and the infinitesimal triangle formed by the differential of the abscissa, the differential of the ordinate, and the differential of the arc length. This characteristic triangle, as Leibniz had called it, is the geometric embodiment of his second postulate, treating an infinitesimal arc of the curve as a straight line. By simple geometric similarity, the slope of the tangent line at that point is shown to be equivalent to the ratio of the sides of this characteristic triangle, specifically, the ratio of the differential of the ordinate to the differential of the abscissa. The problem of finding a tangent is thereby reduced to a two-step algebraic process. First, apply the rules from section 1 to find the differentials for the equation of the curve. Second, form their ratio. The evaluation of this section's claim to universality and simplicity is overwhelmingly positive. L. Hospital applies his method to a series of examples, including the parabola and other classical curves, demonstrating with each one how the problem is solved with remarkable efficiency, where previous methods required ingenious, curve-specific geometric constructions. The analyze offers a single, invariant procedure. The internal logic is flawless. Given his axiomatic starting point, the characteristic triangle and the ratio of differentials provide a direct translation from the language of algebra to the geometry of tangents. The section's primary achievement is its powerful demonstration of the analytic method's superiority. It takes a problem that was a benchmark of geometric prowess and renders it a routine exercise. The work persuades the reader not through rigorous proof in the Euclidean sense, but through overwhelming evidence of its problem-solving capacity. The claim that his method provides a general solution to the tangent problem is fully substantiated by the examples he provides. This section, more than any other, cemented the reputation of the differential calculus as an indispensable tool for the working section for the analysis of curvature through extrema and inflection sections. 3 and 4 of the analyze extend the methods to the more subtle problems of finding maximum and minimum values of a variable, known as extrema, and identifying points of inflection. The claims here are that these geometric properties can also be determined through the purely algebraic manipulation of differentials. For maxima and minima, L. Hospital's reasoning is clear and compelling. A quantity reaches a maximum or minimum value at the point where it ceases to increase and begins to decrease, or vice versa. At this precise turning point, its rate of change must be momentarily zero. Translating this into his analytic language, the differential of the quantity must be equal to zero. Therefore, the task of finding the highest or lowest point of a curve is reduced to finding the differential of its ordinate, setting that expression equal to zero, and solving for the value of the abscissa. He also astutely notes cases where the tangent might become vertical, leading to a differential that is in his treatment of points of inflection is more intricate and reveals a deeper reliance on intuitive geometric reasoning. He defines a point of inflection as a point where a curve crosses its own tangent, changing from concave to convex or the reverse. He reasons that at such a point, the curve is momentarily least curved. This links the problem of inflection to the problem of extrema. He argues that the quantity that determines the concavity of the curve must itself be at a maximum or minimum at the point of inflection. This leads him to consider the differential of the differential, or the second differential. By his prior logic for extrema, the condition for a point of inflection must be that the second differential of the ordinate is equal to zero. This argument, while producing the correct algorithmic procedure, is less a formal proof and more a brilliant intuitive leap. It relies on a qualitative sense of how concavity changes, which is then translated into the language of differentials. The evaluation of this section's claims is that it successfully provides correct and powerful algorithms for finding these key features of a curve. The justification for the maxima and minima rule is direct and persuasive within his framework. The justification for the inflection point rule is more heuristic, but its operational success was undeniable. These sections further solidified the core message of the analyze. The most subtle geometric properties of curves are encoded within the algebraic relationships of their differentials. Section 5, the resolution of indeterminate forms deep within the analyze. In Section 9 lies the treatment of a specific problem that would, through a historical irony, grant L. Hospital his most enduring eponymous fame. This section addresses the issue of evaluating a fraction at a point where both its numerator and denominator become zero, resulting in the indeterminate form of 0 divided by 0. The claim is that the calculus provides a definitive method for discovering the true value of such an expression. The argument L. Hospital presents is a model of geometric clarity. He considers a curve whose ordinate is represented by the numerator of the fraction, and another curve whose ordinate is represented by the denominator, with both ordinates becoming 0 at the same value of the abscissa. He then examines the ratio of these ordinates at a point infinitesimally close to the critical point. Invoking his second postulate, which allows a curve to be treated as a collection of short straight lines. He argues that the ratio of the two small ordinates near the point of intersection will be the same as the ratio of the differentials of the ordinates at that point. This leads directly to the famous rule: the value of the indeterminate fraction is found by taking the ratio of the differential of the numerator to the differential of the denominator, evaluated at the critical point. The evaluation of this claim reveals one of the most elegant applications of his infinitesimal method. The geometric argument is persuasive and provides a clear, intuitive justification for the resulting algebraic procedure. The brilliance of the presentation cemented the rule's utility and ensured its wide adoption. This section is also where the circumstances of the book's creation become most relevant to an evaluation of its claims. It is now well established that this rule, along with much other material, was part of the instruction provided to L. Hospital by his paid tutor, Johann Bernali. The Analyze presents the rule as a seamless part of its author's system, a testament to L. Hospital's skill in synthesis and exposition. The internal claim that the calculus can resolve this indeterminacy is perfectly demonstrated. The procedure is unambiguous and effective. The historical context adds a layer of intellectual wit to the situation, wherein the clarity and prominence of the explanation in the first calculus textbook secured the name of the patron for a discovery made by the tutor. Regardless of its provenance, the section's argument is a powerful validation of the infinitesimal approach. Section 6 demonstrating analytic power with caustics and evolutes. The later sections of the Analyze, particularly those dealing with evolutes, involutes, and caustics, represent the triumphant application of the entire machinery developed in the preceding chapters. Evolutes are the loci of the centres of curvature of another curve, while caustics are the envelopes formed by light rays reflected or refracted from a curved surface. These were problems of immense difficulty for classical geometry, often considered the pinnacle of advanced research. The central claim of these sections is the comprehensive power of the differential calculus to solve such problems with systematic ease. L. Hospital demonstrates how to derive the equations for these complex, second-order curves by applying his differential method. For example, to find the evolute of a curve, he first develops a formula for the radius of curvature at any point, a calculation that itself involves both first and second differentials. He then uses this information to determine the coordinates of the centre of curvature, and by treating these coordinates as variables he derives the equation of the new curve, the evolute, that they trace. An evaluation of these final application sections confirms their status as the book's rhetorical and mathematical climax. They serve as the ultimate proof of concept for the entire enterprise. The internal claims that these difficult geometric constructions can be reduced to analytic calculation are substantiated through detailed and successful examples. The complexity of the results, derived through a uniform and repeatable method, stands in stark contrast to the ad hoc and often cumbersome geometric proofs that would have been required otherwise. These sections function as a persuasive argument from utility. Any lingering doubts a reader might have harboured about the logical stability of the initial postulates would be severely challenged by the sheer power and fruitfulness of the method in action. The Analyze here moves beyond solving known problems more easily. It provides a tool for exploration, empowering mathematicians to investigate and define new families of curves with unprecedented analytic control. These chapters are less about laying foundations and more about building a spectacular edifice upon them, demonstrating that the new analysis was not merely a new technique but a new way of seeing and constructing the mathematical. In conclusion, a direct evaluation of the internal claims of L. Hospital's Analyze reveals a work of profound and dualistic legacy. Its primary achievement, and the source of its immense influence, was the masterful systematization of the Leibnizian calculus into a clear, algebraic, and widely applicable method. Section by section, the work makes and substantiates the claim that the fundamental problems of geometry, from tangents to caustics, can be solved through a unified algorithmic process. The success of these claims, however, is predicated entirely upon a set of foundational postulates that prioritize operational power over logical rigor. The internal coherence of the analyze is impeccable, provided one grants the initial metaphysical commitment to the nature of infinitesimals. The work's genius lies in this very structure. It presents a powerful, self-consistent system whose practical successes were so overwhelming that they temporarily silenced foundational objections. In making the axioms of the early calculus so explicit, L'Hopital not only created the textbook that would teach the method to a generation of European mathematicians, but he also articulated with perfect clarity the very logical problems that would motivate the subsequent development of analysis by figures like Lagrange, Bolzano, and Cauchy. The analyze is thus the defining document of 18th century calculus, a monument to a period of extraordinary analytical creativity, sublime confidence, and a willingness to build magnificent structures on intuitively grasped, rather than rigorously proven, foundations.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.